Okay, good morning students. We'll start with the today's lecture. Okay, lecture number 23. Already we have seen the unit step response of first order system, second order underdamped system, then numericals also we have solved. Then we'll see the time response specifications and the derivation of these time response specifications. There are several time response specifications with respect to the second order underdamped system, right? Okay, we'll see what are these time response specifications and we'll see the derivation, right? Derivation of the expression for TR means rise time, TR, peak time, TP, MP means peak overshoot, TS means settling time, ESS means steady state error. We'll see all these things with respect to this time response specifications. Okay, we'll start time response specifications, and you can observe in this unit step response of the second order system for the second order underdamped system. So this is time axis t, this is the response c of t, then this is the unit step input, right? This is the unit step input and this is the unit step response curve for different time, right? So it increases and slowly damped oscillations we are going to get. So this is the unit step response curve of second order underdamped system, second order system, that to underdamped system, underdamped system. Okay, with respect to this unit step response curve of the second order underdamped system, we will analyze some time duration or time response specifications. There are several things I have mentioned here. From here to here, from this time to this time I will call it as delay time. From here to here I will call it as rise time. From here to here I will call it as peak time. From here to here I will call it as peak overshoot. From here to here I will call it as settling time. And what are these and how they are defined? So this TR, TD, TR, TP, TS, MP, all those things we will see, and these we call it as time response specifications. And what are these? And we will try to define them with respect to this diagram, right? Then only we will understand. Then there are something called as overshoots and undershoots and peak overshoot. You can observe here, just overshoot. This is my unit step input. This is one, right? This is my unit step input, right? Then with respect to this, the response is crossing this unit step input. So this is first overshoot, first overshoot, first overshoot, right? Then this response is crossing this unit step input below. It is this was above and this is going below the unit step input. So this we call it as first undershoot, first undershoot, right? So I hope you came to know what is overshoot and undershoot. The response just above the unit step input we call it as overshoots. The response below we call it as undershoots. This is first overshoot. Then we'll come to the second. This is second overshoot, second OVS overshoot. Just OVS I will write, overshoot. Then this one is second undershoot, second undershoot, right? This one is third overshoot, and this is not third overshoot because, right, this is third overshoot, and so on, right? It continues. Okay, I hope you came to know what are overshoots and undershoots. Then what is peak overshoot? So the first overshoot itself is the peak overshoot. That we'll see. We'll define all these things, right? I hope you came to know briefly. Okay, just we'll start with these few points. Control systems are generally designed with damping less than 1, that is oscillatory step response. Means for underdamped second order underdamped system we are taking, Z is always lying between 0 to 1, right? Z lies between 0 to 1. So if Z is less than 1 or Z lying between 0 to 1, those are underdamped systems and the response is damped oscillatory like this, right? And what about the poles? The poles are complex conjugates. They lie on the left of the S plane, right? That also we have seen. And why we take generally for only for underdamped systems means the response is very fast. You can see here, yes, the response is rising towards this final value very fast, and finally the oscillations are going to die out at time t equal to infinity, right? So we prefer these second order underdamped systems. And why high order control system means more than second order. I mean, if I go for third order system, fourth order, fifth order, so what is their behavior? All those things we have to see. You will see. Higher order control system usually have a pair of complex conjugate poles for damping less than 1 which dominate over other poles. If I take the third order system or fourth order, fifth order, one of the pair of poles will be complex conjugate poles. Just like for second order system, the poles are complex conjugate, right? If I take the third order or fourth order or fifth order system, the poles will be complex conjugate poles. One of the poles will be complex conjugate poles and they are the dominant poles. Means they will get the stability of the system. And the response what we are going to get if I take third order or fourth order or fifth order, the response is damped sinusoidal oscillations only. That's the nature of response will be like this only. Damped sinusoidal oscillations, right? Whether it is so, we can say that the second order system is the representative of the all the higher order system, third order, fourth order, fifth order, and so on, right? So we will restrict our study only for the unit step response of second order underdamped system, not for third order, fourth order, and because they are representative and they behave like second order system only for z less than 1, for z lying between 0 to 1, right? Okay. The time response of second and higher order control system to unit step input is generally damped oscillator net, already I have told, as shown in this figure, right? Okay. Just now I introduced you few time response specifications, TD, TR, TP, TS, MP, all those things we will define in the next slide. Time response specifications. So the transient response specifications are as follows, because why we call this TD, TR, TP, TS all as transient response specifications means because the every system, the response of the system C of t consists of two parts, the transient response CT of t plus the steady state response CSS of t. Right? When this steady state will be coming at time t equal to infinity, it will attain the steady state at time t equal to infinity. Before attaining the steady state, so these specifications, this is the transient response, right? So here this is transient response in this part CT of t. After this it is CSS of t, because the system is at time t equal to infinity, it is achieving the final steady state value. So before achieving the steady state, these time response specifications we call it as transient response, time response specifications. So hence we call it as the transient response specifications are as follows for underdamped second order system. So we'll define one by one. Delay time, TD. We can observe here delay time from here to, if time is from here to here, it is achieving 0.5 means 50% of the final value. 1 is 100%, 0.5 is 50%. Means how to define this delay time? The delay time is the time required for the response to reach 50% of the final value the very first time. We call it as delay time TD. Right? The time required by the system to achieve 50% of the final value. We call it as delay time from here to here. Right? So this we have taken from here to here. It is delay time TD. Over. The next rise time. TR. Just observe here. Rise time from here to here. Means the system is achieving 100%. Right? It is varying from 0 and it is achieving till 1. And this corresponding time we call it as rise time. How to define it? We will see here the rise time. The rise time TR is time required for the response to rise from 0 to 100% of the final value for underdamped system, right? From 0 to 100% it is achieving in this time duration. Hence we call it as rise time. Delay time to achieve 50% of the final value, then rise time to achieve 100% of the final value. That duration we call it as rise time. Is it fine? Then next we will take up the peak time TP. Observe here. Yes, the response is varying here and it will achieve the maximum peak value. In order to achieve that maximum peak value, the time taken is nothing but the peak time TP from here to here. It is the time taken in order to achieve the maximum value, right? This is the maximum value. You just see, if you compare with any other values in the amplitude of the variations of the sinusoidal wave, then you can observe here, this is the maximum value. The time taken by the response to achieve this we call it as first overshoot also, right? Time taken by the response to achieve the first overshoot or maximum peak value, we call it as TP, peak time. So how we will define it, we'll see. The peak time TP is defined as the time required for the response to reach the first peak of the overshoot or first peak overshoot, right? First peak overshoot we have defined. What is that first peak overshoot, right? And next we'll see the peak overshoot MP. Peak overshoot MP. Just observe here. This distance from here to here, this is the reference, this is the unit step input, right? So this is the reference and the first overshoot means the difference between the first peak overshoot and the reference input, we call it as peak overshoot MP. How to define it, we'll see. From here to here, this distance, right? This is MP from here to here. So this we have taken, this here they have shown MP, peak overshoot. Is it fine? So how to define it, we'll see. It is the maximum peak value of the response curve, that is first overshoot. Maximum peak value means it is first peak overshoot, right? It is the maximum peak value of the response curve measured from unity. Measured from unity means this is the unity, right? This is my reference, unity. It is measured from unity to the first peak value or first overshoot. Is it fine? So it is the maximum peak value of the response curve measured from unity. Then next, suppose how to define peak overshoot in other cases. If the final steady state value of the response differs from unity, right? If the final steady state value is not unity, if it is other than unity, then what is the formula or percentage peak overshoot will define for such kind of things if it is the reference is other than unity. So always we see for reference unity only, other than unity will not see, but let us have a look at the formula, right? If the final steady state value of the response differs from unity, then it is common to use maximum percent overshoot, and it is defined by C of Tp minus C of infinity by C of infinity into 100. If it is other than unity, if it is unity, what will happen? I will tell you. C of Tp as it is, yes, C of Tp minus C of infinity. If it is unity means at time t equal to infinity, the system is going to attain the steady state value. What is the steady state value? C of infinity is 1 only, right? C of infinity is 1 only, because at time t equal to infinity, the system will attain the steady state value or final value. So for reference as unity or for unit step input, so C of infinity is 1 divided by 1 C of infinity into 100. This is the formula what we are going to get. If it is other than unity means, if it is, what is the value other, what is the value corresponding value you have to write. At time, if it is 2, you write down 2, right, based on that. I hope you are getting. So if it is other than unity, maximum percent overshoot is defined as C of Tp, means at time t equal to Tp. At time t equal to Tp, it will achieve the maximum value, right? So C of Tp minus C of infinity by C of infinity into 100, right? Okay, the amount of maximum overshoot or percent overshoot directly indicates the relative stability of, means the system is stable, because already the unit step response of second order system is stable. Because why we call it as this as stable system means at time t equal to infinity, the oscillations are going to die out and system will achieve the steady state value or final value. Hence we call such type of system as stable systems, right? So if the system is stable, whether it is less stable, more stable, the degree of stability means that we call it as relative stability. Relative stability means the degree of stability. The system is already stable. To what extent it is stable, whether it is less stable, more stable. So this degree of stability and relative stability we will try to understand in the next coming chapters, right? So, but to understand that relative stable system is already system is stable. Whether it is less stable, more stable, with that we have to judge or decide. That's all, right? Okay, that we'll see it. We'll try to understand this concept, relative stability concept, in the coming chapters, right? Then settling time, Ts. We denote it as Ts. So observe, we'll see here through this diagram. With respect to this time response specification or unit step response curve of second order system, we have to define all these time response specification. Already we have defined delay time Td, rise time Tr, peak time Tp, and peak overshoot Mp. The next settling time Ts. Observe here, from here to here. You observe, yes, the response is rising, it is going attenuation, and finally you can observe here it settles down here, and we are taking the tolerance band here, dotted line. This is the unit step response. Above it we are taking one reference, below it we are taking one response. If this is 100%, if I let me define it as plus or minus 2%, plus or minus 5% tolerance band means, if it is 100 means, if it is taking tolerance band is plus or minus 2% means 98 to 102, 98 to 102. If I say plus or minus 5% tolerance band means 95 to 105. I hope you are getting. So let me choose, I can choose 2% tolerance band or 5% tolerance band, right? And if the response lies within this tolerance band, here you can observe this here, this is my reference tolerance band. Here if you observe, here it is crossing the tolerance band, here also it is crossing the tolerance band, but here if you observe, it is lying within this tolerance band. You can observe there, right? This, if you take it, yes, it is in the tolerance band only. If I take this overshoot, it is also lying in the tolerance band. Means, then how to define the settling time? I'll tell you. Observe here. The settling time is the time required for the response curve to reach and stay within a particular tolerance band of 2% or 5% of its final value. Means the time taken by the response to reach and stay within the particular tolerance band. This is the tolerance band, right? Yes, here at this, if I take this instant, the response is crossing this tolerance band here. So it is not achieving the steady settle. It is not, the response is not settling within the tolerance band here. So if I consider this tolerance band here at this time, yes, the response is settling within this tolerance band of plus or minus 2% or 5%. So hence the time required for the response to reach and stay within the tolerance band, available tolerance band of plus or minus 2% or plus or minus 5% is termed as the settling time TS from here to here. I hope you are getting. This is the TS. So just once again we will define settling time is the time required for the response curve to reach and stay within a particular tolerance band of plus or minus 2% or 5% of the final value. Then steady state error ESS. It is not shown in the diagram, but we know what is steady state error. Observe here. Yes, yes, I will continue with this only. Yes, this is the actual desired value unit step input. If the response, let me change the ink color. If the response at time t equal to infinity, if it does not achieve, so this is the, let me assume that this is the desired output, desired, if this is the actual one, then there is a steady state error. But we have seen already in the derivation, for steady state error for first order and second order system it is 0, means the system is going to achieve the steady state value, means there is no difference between the desired output and the actual output, right? So that we are going to define it as steady state error. So ESS we call it as steady state error ESS. So it indicates the error between the actual output and the desired output as the time t tends to infinity. So ESS is equal to limit t tends to infinity E of t. This, what is this E of t? It is the difference between the actual output, desired output is R of t and actual output is C of t. So R of t minus C of t. I hope you are getting this, right? So E of t is nothing but the actual desired output minus the actual output, R of t minus C of t. So limit t tending to infinity. So finally, to define the steady state error, it indicates the error between the actual output and the desired output. If steady state error is 0, means the system is going to attain the steady state or final value, hence the such kind of systems are stable systems, right? Okay, next, understanding all these time response specifications, and we will make one statement here. In most cases, it is desirable that transient response must be sufficiently fast and be sufficiently damped. Means always we choose the value of z to lie between 0 to 1. So z can take 0.1, 0.2, 0.3, 0.4 till 0.9. But in that various values of z, that is, for example, let me take 0.001 or 0.002, then 0.1, 0.12, 0.2, and so on, 0.3, and so on till 0.99. Let me take, right? These values of z are lying between 0 to 1 only, out of which I want the behavior should be as per my requirement. Means it should behave, we should be in a position to predict the nature of the output. So which is the desirable value of z? Z should be always between 0.4 to 0.8. That would be better. If the value of z lies between 0.4 to 0.8, then the system will behave properly. Then I can predict the nature of the response of the system. So in most, just I'll read out this. It is desirable that the transient response be sufficiently fast and be sufficiently damped. Thus, for a desirable transient response, means in order to get the desirable transient response, the damping ratio must be between 0.4 to 0.8. For larger values of z, means for z greater than 0.8, the system responds slowly. But since I want the fast response and sufficiently damped, means the oscillation should die, damped means. So for that, z should lie between 0.4 to 0.8. This is the desirable, 0.4 to 0.8. Then the system will be fast and it will be suitably damped. Fast and damped. Fast and damped. For z lying between 0.4 to 0.8. So this is underdamped system only, but the desirable, because in order to get the desirable transient response, z should lie between 0.4 to 0.8. This is the desirable values of z or damping ratio. Then next we'll see the derivation. Yes, a derivation of expression. Yes, we have seen all these time response specifications, right? Delay time. Let me change the ink to back to red only. Yes, delay time, rise time, peak overshoot, settling time, right? We will derive for each and everything. How to, so we'll see the derivation of expression for rise time, peak overshoot MP, settling time TS, the steady state error ESS, right? All those things one by one we will take up. The first derivation of expression for rise time TR, right? So we'll see. Okay, see, this is, see what are the derivations we are doing. These all things are for second order underdamped. Please keep in the mind. Second order underdamped system. Underdamped system, and that to input is unit step. Second order underdamped system subjected to unit step input. Subjected to unit step input. So please keep in the mind, right? Whatever the derivations we are doing with respect to the second order underdamped system subjected to unit step input, right? All those things we'll see. So derivation of expression for rise time TR. Then yes, rise time TR, we will derive it. So the second order system is subjected to unit step input, right? And what is the unit step response of the second order system, right? We already know this. I have told C of t, variety of forms. This is one of the form. This we know it. Already we have derived it. The unit step response of second order system. This is one of the form, right? We know this. Yes, we have done unit step response of first order system. We have obtained C of t, right? What is C of t for first order systems? 1 minus e to the power of minus t by t. This is for first order system. Similarly, for second order system, this is the unit step. This is one form. There are several other forms also I have shown you, right? So the unit step response of the second order system is given by C of t is equal to 1 minus e to the power of minus z omega n into t divided by root of 1 minus z square into sine of omega dt plus theta. Call this as equation 1. Here they called it as 4.1. No problem. We call this as equation 1. Then what is rise time? You can observe here, we have defined here what is rise time. See here, in the time taken by the response to reach from 0 to 100% of the final value. So this we call it as rise time TR, 0 to 100% of the final value, right? Okay, at time t equal to TR, C of t is 1, C of TR is 1, right? At time t equal to TR, what is the value of C of t? C of t here, right? C of t is nothing but t equal to TR, right? C of TR equal to 1. So by definition of rise time, we know that the time taken by the output rise from 0 to 100% of the final value. So at time t equal to TR, C of TR is 1. We will make use of this, right? So at time t equal to TR, so C of TR, what is the C of TR? It is equal to 1. So on LHS, I'll substitute this as 1. And RHS, I'll write this as it is, 1 minus e to the power of remaining thing as it is. Then next, take this onto left hand side and move this one this side, right? So this one 1 minus 1 is 0. So e to the power of minus z omega in t. What is t? T is nothing but tr. We have substituted. Substitute the value of for t. You substitute t equal to tr. So we have substituted here t equal to tr. And sine of omega dt t equal to tr. We have substituted, right? So 1 minus 1 it will be 0. Take this side. So this entire thing is 0. But observe here whether this term should be 0 or sine term should be 0. Which one? There are two terms. One is exponential decaying exponential term and another one is sinusoidal. So which should be 0? Observe the rise time here. Observe rise time. So the response is slowly rising. Are there any oscillations? There are no oscillations. Means this term should be equated to 0. Because there from at time from 0 to TR, there are no oscillations. Oscillations are starting after TR like this. But from time 0 to TR, the response is rising slowly, exponentially, right? So this exponential term cannot be 0 because the response is exponential in nature. This cannot be 0. Only this can be 0. Sine of omega dt TR. So we will liquidate the second term to 0. So in the next slide, we will liquidate this to 0 because you can observe at time t equal to 0, the response is rising slowly, but there are no oscillations. You can observe here. Is there any oscillations here? No. So we will liquidate the sine of omega dt TR plus theta equal to 0. So we will liquidate it. Okay, 1 minute. Yes, this cannot be 0, first term. So I have written this. The first term cannot be 0. But second term, sine of omega dt must be equal to 0. This I have said. So equate this. Sine of omega dt TR plus theta equal to 0. And this is equal to why only sine pi? It can be sine 0 also, no? Why only sine pi? Observe here. I'll tell you. Observe here. For second order underdamped system, the poles are complex conjugates here. Right? These are complex conjugates. And let me draw this triangle also here. Right? Right? So the poles are complex conjugates for value of z lying between 0 to 1. And you can observe here 0 degree. So we will take 0 degree. This is 90 degree, 180 degree, 270 degree, we are measuring the value of theta in the anti-clockwise direction. If I measure the angle in anti-clockwise direction, it is positive 0, plus 90, plus 180, plus 270 and 360, right? So observe here, since the poles are lying in second quadrant, in second quadrant means if I take 0, sine 0 is 0, it will come in first quadrant, but the poles are lying in second quadrant, so sine of 90 is not 0, sine of 90 is 1, so it is sine of 180. So take sine of 180 degree because the poles are lying in second quadrant. So say don't take sine 0 here, sine of 180 degree, sine of pi is nothing but sine of 180 degree, right? So sine pi, so sine pi equal to 0, right? So uh, yes, then sine can be removed on both the sides, then right, then omega dt tr plus theta is equal to pi. So omega dt tr equal to, take this theta, pi minus theta, then what is tr equal to pi minus theta by omega d. So this is the expression for rise time. Expression for rise time tr equal to pi minus theta by omega d. Then what is omega d? It is damped natural frequency. We know that omega d is equal to omega n into under root of 1 minus z square. Then what is this theta? Looking at this diagram, so this opposite sign from here to here, it is omega d. Here they have mentioned here, this is omega d, and that is equal to omega into under root of 1 minus z square. Then what is this theta I want? Tan theta equal to opposite by adjacent. So this is omega d divided by z. This is z omega n. So omega n root of z 1 minus z square divided by omega n, z omega n. Omega n will get cancelled. So theta is equal to tan inverse of root of 1 minus z square by z. This is the value of theta. No need to substitute here. So take this, only this form. Don't go by this. We will leave this because we know what is theta and what is omega d. By looking at this diagram, we can calculate, right? So the rise time tr is equal to pi minus theta by omega d. And you try to remember this triangle. Just I will draw the triangle separately here, so that that will be helpful for us later. So complex conjugate pole, draw this. Let me take some other ink. Yes, we'll join it here, and this is theta. So this value is z omega n, and this value from here to here, height is omega d, that is equal to omega n into under root of 1 minus z square. From here to here, it is undamped natural frequency omega n. All the three sides we should be knowing. So what is tan theta? Tan theta equal to opposite by adjacent. So omega opposite is omega n divided by root of 1 minus z square. Adjacent is z omega n. So omega n will get cancelled. So theta is equal to tan inverse of root of 1 minus z square by z. The same thing has been written here. Is it fine? So whenever we are taking second order underdamped system, please you try to remember this location of poles and this diagram, because we will be using this in the further derivations also. Please keep in the mind, right? Okay. We have derived the expression for rise time tr, and it is equal to pi minus theta by omega d. I hope you understood. If any doubts are there, please unmute yourself and talk to me so that I can clarify your doubts immediately. Hope so. Yes, nobody is unmuting. I hope so you understood. Then we will proceed with the next derivation, right? So derivation of expression for peak time. Let me change the ink. Derivation of expression for peak time TP, right? Once again, second order system subjected to second order underdamped system subjected to unit step input, right? We'll see. Yes, in order to derive for peak time TP. Yes, we know this already. This is the unit step response of second order system subjected to unit step input. This expression only will take. So C of t is equal to 1 minus e to the power of minus z omega nt divided root of 1 minus z square into sine of omega dt plus theta. This we know, right? Then what is the definition of peak time? We will try to make use of definition of peak time. You can observe here in this diagram, the response is rising, peak time from here to here, right? Observe here, and it is reaching the maximum value. So if I consider what is the slope at this maximum value, slope will be 0 at maximum value because it is parallel to this, right? So slope is 0. If I take point somewhere here, it is having some slope, but if I take it here, the slope is 0, means at time t equal to tp, the slope is 0. So we'll make use of the slope concept and try to derive the expression. We'll see here, the peak time, we'll define it. Peak time is defined as the time at which the maximum value of the magnitude occurs. Yes, maximum value of the magnitude occurs. This is fine. Therefore, at time t equal to Tp, the slope of C of t must be 0 because it is parallel, right? So the slope of C of t must be 0. So in order to get the slope, we will derive it. We know the slope is equal to d by dt of, take the derivative of the response C of t at time t equal to Tp. So we will take the derivative of C of t. So yes, derivative of C of t at time t equal. So derivative of 1, this is vanish. This minus sign, keep it as it is. This minus sign. So I will derive here. Observe here. Already I have written here. How this will come, I will tell you. I will derive it and show you here. So derivative of 1 is 0 minus open bracket. So this is the first function, right? So let me yes, 1 minute. Yes, we have to derive with respect to time t. So minus 1 by root of 1 minus z square is common. We'll take it outside because this is constant, right? So this is one function and this is another function. Keep first function as it is, omega nt. Then derivative of second function. Derivative of second function is derivative of sin theta is cos theta, right? Cos of omega dt plus theta. But this is not fully right. We have with respect to time t since, so omega d will also come into picture into omega d plus keep second function as it is. We will keep the second function as it is, sine of omega dt plus theta into derivative of first function, that is e power minus. So derivative of minus e to the power of minus z omega nt is e to the power of minus z omega nt, but with respect to time t means minus z omega n. So we will get this. Then multiply this minus 1 by root of z square and we will get this. I have written here minus e to the power of minus is root of into cos of omega dt plus 2 into omega d, the same thing first term. Then second term minus into minus, because this minus is there, no, this minus it will be minus, so this minus into minus it will be, oh yes, it will be plus only, but this minus it is there, they have written like this only. Same second term, sine of omega dt plus theta into e to the power of minus z omega nt by root of 1 minus z square to at time t equal to Tp, right? So wherever t is there, we'll substitute at time t equal to Tp. In the next, you can observe here, yes, take this common, e power minus z omega nt, this is common. Take this common and move that side, it will be 0. So I am left out with cos of omega dt plus theta, all those things. We will write it here. First we will write this. Minus into minus, it is plus. So z omega n they have written here. Sine of omega dt plus theta. Yes, this is fine. But t equal to Tp. Substitute t equal to Tp. They have substituted here. Then next, this first term minus. What is this omega d? Omega d is nothing but omega n into under root of 1 minus z square. They have substituted. Then cos of omega d. T is nothing but Tp plus theta. I hope you understood. If any doubts, you can ask. From differentiation I have done here, and multiply and you will get this, and substitute time t equal to Tp. So you will get this. Then next, now what they have done, they have taken omega n common from here, omega n, and it is omega n will vanish because it is 0. Then remaining terms they have written here, z sine of this omega n will vanish. So z sine of omega d Tp plus theta minus this, right? I hope you understood this. Then next, you can see here, already I told, please keep this diagram in the mind, this triangle, because for second order unredamped system, the poles are complex conjugates, they lie in the left half of the S plane. This is S plane, right? This already I have told you, sigma plus j omega. And you keep this diagram in the mind. What is this z? Cos theta equal to z, because cos theta equal to adjacent by hypotenuse, z omega n by omega n. So it is z only. So for z, you write substitute cos theta from the triangle, right? So z is nothing but cos theta. This sin theta they have written as it is, minus root of 1 minus z square. Root of 1 minus z square is nothing but sin theta, because sin theta equal to opposite by hypotenuse. So opposite is this omega n by root of 1 minus z square divided by omega n. Omega n will get cancelled. So sin theta is root of 1. So substitute for the root of 1 minus z square as sin theta. We have substituted here this cos as it is. Then we know the formula, sin of a plus b. Sin a cos b plus cos a sin b. Sin of a minus b here. Minus is there, right? So this is a and this is b. Sin of a minus b. This is a minus b. I hope you are getting sin of a minus b. And it is equal to 0, right? But How you will get 0? It is sine of pi only. It is not sine of 0 because the poles are lying in second quadrant. In second quadrant means it should be 180 degree, not right. So sine of 180 degree. It is nothing but in radians. Sine pi radians equal to 180 degree. So equate this. Theta will get cancelled. Omega d Tp equal to pi. So what is Tp? Tp equal to pi by omega d. So Tp equal to pi by omega d. What is this omega d? Omega d equal to omega n into under root of 1 minus z square. So we have derived the expression for peak time. This triangle I have shown you for reference here. So this is z omega n. This is omega d. That is omega n into under root of. This is omega d. And this is omega n. I hope the same triangle, right? So the peak time Tp is equal to pi by omega d. I hope you understood this. Then next, this is for first overshoot because peak overshoot Tp. This is in order to achieve the maximum value or first overshoot. If it is second overshoot, third overshoot, what is the formula I am going to get? This is for first overshoot, pi by omega d. Then first undershoot. This is first overshoot. For first undershoot, just multiply 2 times pi by omega d. For second overshoot, 3 times. For the second overshoot, 4 times. This continues. So 4 times pi omega d and this continues. Right? So first overshoot, it is pi by omega d. Whatever I am writing here, just observe here, pi by omega d. This is Tp. This is for first overshoot. Then if I come to the first undershoot, that is 2 times of pi by omega d. This is for first undershoot. Then if I come to the second overshoot, it is 3 times pi by omega d. There is no derivation for this, just this continues. This formula holds good for overshoot. Then if I come to the second undershoot, 4 times pi omega d, and this formula continues. Right? The same thing has been written here and so on. Right? Okay. We have derived the expression for rise time and peak time. Just we will list out what is the expression we got for rise time, pi minus theta by omega d. This is for rise time, and expression for peak time, pi by omega d. So we have seen 2 derivations. The remaining 3 derivations we will see in the next class. So rise time is pi minus theta by omega d, and the expression for peak time is pi by omega d. So we will stop our discussion here only. I'll stop.